Let's jump right into this explainer and crack the case of the missing numbers. If you've ever felt that familiar sense of dread trying to solve for an elusive x, don't sweat it. We're going to look under the hood of Chapter 3 from our source material and see how algebra actually works using the ultimate mathematical tool, balance. So before we start throwing formulas around, we have to ask ourselves, how do we systematically uncover a completely unknown number without just, guessing blindly? It's a fascinating question. Our source material basically frames this like a detective story. We get a set of clues and we need a reliable, repeatable method to follow that trail and find our missing suspect. Here is our roadmap for today. 1. Open and closed sentences. 2. Balancing linear equations. 3. Solving equations step by step. 4. Understanding linear inequalities. And 5. Real-world math applications. Let's get into it. Section 1. Open and closed sentences. Identifying statements. You literally can't solve a problem if you don't know what kind of statement you're looking at. Think of a closed sentence like a completed puzzle. 5 minus 2 equals 3. We know all the facts, and it's definitively true. But an open sentence, like x minus 2 equals 3, well, that's an open case. There's a hidden suspect lurking right there in the form of the letter x, and we can't say if the sentence is true or false until we figure out what that x actually represents. In algebra, that hidden suspect is called a variable. As our source defines it, a variable is simply a placeholder for a value we need to discover. It's a letter or symbol, usually x, but hey, it could be y, a, or p, used to state a quantity that is currently unknown. The whole goal of a linear equation is to transition that open sentence into a closed true sentence by figuring out exactly what value the variable is hiding. Section 2. Balancing linear equations, keeping the scale even. Now that we know what variables are, let's talk about how to handle them. Imagine a physical scale. If one side has a mystery box, that's our x, plus 2 wooden blocks, and the other side has 8 wooden blocks, they're perfectly balanced. The equal sign in our equation literally means weighs exactly the same as. So how do we isolate that box to find out what it's worth on its own, without tipping the scale? This brings us to the absolutely crucial golden rule of linear equations. Whatever you do to the left side, you must do to the right side to keep the scale balanced. If you take 2 blocks off the left side to get that mystery box all by itself, you have to take 2 blocks off the right side too. In math terms, you're applying the inverse operation equally to both sides of the equal sign. This is the absolute bedrock of algebra. Section 3. Solving equations step by step, working backward. Let's see how our source puts this balancing act into practice with a slightly trickier case. We've got 4x plus 9 equals 29. In this scenario, our variable x is being multiplied by 4 and then increased by 9, all balancing out perfectly to 29 on the other side. To solve this, we just have to work backward to isolate x by applying our balancing rules. Let's strip away the layers. First, we get rid of the loose numbers. We subtract 9 from the left side, which means we must subtract 9 from the right side. Our new balanced equation is 4x equals 20. Okay, now x is being multiplied by 4. To undo that, we divide the left side by 4, and again, to keep that perfect balance, we divide the right side by 4. 20 divided by 4 is 5, so x equals 5. Mystery solved. Section 4. Understanding linear inequalities when scales tip. We've totally mastered the perfectly balanced scale, but what if things are intentionally tipped to one side? When things aren't perfectly equal, we use linear inequalities. Instead of an equal sign, we use these 4 distinct symbols to tell us exactly which way the scale is tipping. Less than, greater than, less than or equal to, and greater than or equal to. These little symbols open up a completely new world of mathematical modeling. What's really fascinating here is the contrast. An equation gives you one exact suspect. If x equals 4, then x is exactly 4, nothing else. But an inequality, that gives you a whole lineup of possible answers. If x is greater than 4, the answer could be 5, 10, or literally a million. Our source shows equations as a single, solitary point on a number line, while inequalities open up an entire shaded region of infinite possibilities. When solving inequalities, you're going to use the exact same balancing steps we just talked about, but with one massive exception. You have to beware of this trap. The inequality golden rule states that if you ever multiply or divide an inequality by a negative number, the whole balance of the number line reverses. This means you must literally flip the inequality symbol. So if negative 2x is greater than or equal to negative 18, dividing both sides by negative 2 flips the sign, giving you x is less than or equal to 9. It's a tiny detail, but forgetting it will completely derail your investigation.
Section 5. Real-world math applications. Math in action.
So when are you actually going to use these balanced and tipped scales outside the classroom? Well, every time you open up a navigation app, you're interacting with inequalities. Our source material highlights a great example, mapping a route from Ashe to Lumping. When the app estimates the trip will take, say, 12 hours or less, depending on traffic, it's calculating a real-world linear inequality right behind the scenes. The travel time, variable t, is less than or equal to 12. Inequalities govern time limits, speed limits, and safety capacities everywhere around us.
Or consider a landscaping project drawn from our source's competency tests. Imagine you have a triangular garden. 2 of the sides are known, 3 meters and 5 meters. The third side is unknown, labeled as the expression x plus 2 meters. Now suppose the total perimeter, the fencing around it, must be at least 60 meters to keep the local wildlife out.
We can actually translate that entire physical problem into a simple inequality model. 3 plus 5 plus the quantity x plus 2 is greater than or equal to 60. By pulling those physical measurements into this model, we can simplify it. Combine the numbers on the left to get 10 plus x is greater than or equal to 60. Subtract 10 from both sides, and we find that x must be greater than or equal to 50. Just like that, algebra helps us figure out exactly how much material we need to buy to make the project work.
Whether you're estimating travel time, budgeting for groceries, or building a garden, you are constantly solving open sentences in your head. Algebra is really just the logical art of making those invisible calculations visible. So, the next time you look at the world around you, ask yourself, what hidden variables are currently tipping the scales of your life without you even noticing?